So welcome to our official start of data structures for today. Today we're going to, well, let's see, last time we talked about the heaps, the min heap versus the max heap, and how the run times of that compare to the AVL tree and the different operations that it's able to do. And in particular, the key thing to remember is that the AVL tree basically supports everything: insert, delete, find, whatever you want, anywhere you want. But the heap only supports the finding min or finding max, and you can't find or delete from arbitrary locations in the tree. The advantage of that is that we get slightly faster performance, both asymptotically and constant factor. Today, what we're going to talk about is some of the tools that you'll need for integrating your entire containers repository into a single project that you can that will get posted online where people can install it. And then we'll also talk about something called a hash table. And this is actually how Python implements their internal data structures, like the dictionary and the set. And so we'll compare their implementations to the ones that you all have done and see the advantages and disadvantages of both. So I'll start now, share my screen. And to start with, I have the our issues tab pulled up. I just wanted to comment again on this issue about the data mining class. That are where we're at with that is we have a couple of other classes that we've picked out as they would be approved from our end, from CMC's end, approved substitutes for the data mining class. And we're just working on talking with the instructors in those classes about getting seats available for students. So that's one thing that we're doing. And the other thing is also looking at trying to get the funding together to hire somebody to teach that class separately. So those are the two things that are going on. No concrete solutions yet, but still working on it. I also want to remind you that you have the required reading and viewing assignment still due. Again, you have until the end of the semester to do that. The actual final due date will be the same day that the final exam is due, so the last day of finals week. I would recommend that you try to get these done before then, though, so that you're not totally in crunch time during finals week and trying to squeeze in something like this. For this class, your next homework assignment is going to be a relatively light one. So this coming week would be a good time to try to do these, watch these videos if you haven't done that already. So with that said, we're gonna switch over to so currently we're on week 12 of the class, but I'm going to take us to the week 13 repo for a second so that we can take a look at your next week's homework assignment. I've already posted it so you can get a sense of what you'll have to do, and you can even get started and go ahead and complete it if you'd like. The basic idea of this homework assignment is that you're going to take your full containers repository, this thing that we've been working on for the past month or so, and you're going to put it in this place called PyPy, the Python package index. And this is the place that whenever you do a pip install command, it's looking at this PyPy package index in order to actually find the package and install it. So after you go through the procedures of this homework assignment, anybody anywhere in the world will be able to run the command pip3 install, then the name of your package, and be able to download it on their computer and get access to your AVL tree and heap and binary search tree. In order to get full credit on this assignment, it doesn't matter, like you don't have to pass there's no test cases to pass. So if you say missed something in the AVL tree or the heap assignments, you're not going to get double counted as missing points for this. Instead, if you just get something up there that other people can install, that's going to be the marker of a full credit solution. Even if your package isn't 100% fully correct, as long as people can install it and use it, then you'll get full credit. So the tasks, the particular tasks that you'll have to complete are first, this one right here. This is a task inside of Git itself, where you'll be merging all of your branches together back into the master branch. So we've been really careful so far at this point of keeping all of these separate components that you've been working on separated out into different branches. And it's been a little bit of an artificial sort of restriction that we've done for this project. But when you're actually working on real projects, whether you're working by yourself, if it's a larger project, or working with other people, this sort of workflow of anytime you're working on a new feature, create a branch for that feature, put some test cases in that branch, and then make those test cases pass. And once those test cases pass, merge it back into the master. That's sort of the standard workflow that people do when they're working with Git. And so you've gotten a lot of practice with that workflow over the past month. The next thing that you'll have to do is create a license file in your repo. The license file is in some sense the most important part, the most important file in your repo, because this file describes how other people are allowed to use your code. If you do not have this license file, then it is technically illegal for anybody to use your code, even though you've put it online. It's illegal for them to use it for any purpose. Essentially, this license file describes what sort of purposes other people are allowed to use the code for. And so one of the gotchas to sort of keep in mind when you're looking at GitHub repos in the future is if you don't see a license file in that Git repository, then implicitly the maintainer of that repository has said you are not allowed to use this code. You're allowed to read it and reference it, think about it, but you're not allowed to use it, copy and paste it. You're not allowed to run it unless you have explicit written permission from them. And this is the current sort of legal standard in the US and the vast majority of countries around the world. So we have to, as part of our project, we're going to pick one of these license files and put it in the repo. What you'll have to pick in particular is an open source license. And we sort of define an open source license as satisfying these two criteria right here. So the first thing is that anyone can use the software for any purpose, that there are no restrictions on what the software can do. So personally, I am pacifist, not a big fan of the US military, but when I create open source software, that software is allowed to be used by the US military, and they're allowed to do with it whatever sort of military things they like to do, even though I personally disagree with that. And that's just sort of one of the requirements of open source software. A lot of people don't like that requirement and so choose not to release their software as open source because they want to have some control about the future purposes that people are going to do with their software. The other requirement for something to be open source is that source code is provided with the software. So putting your repository on GitHub automatically satisfies the second requirement, but doesn't necessarily satisfy this first one. There are a few common examples of license files. These three right here are just ones that you should know, that people will talk about them all the time. And so the first one is the BST3 license or the MIT license. These two, they're technically different licenses. So MIT comes from the famous university, MIT in Boston. BST, B here stands for Berkeley. So this is the Berkeley Standard Development License, and this comes out of Berkeley. The conditions of these two licenses are essentially exactly the same. The only difference is that this is sort of the West Coast version of the license. This is the East Coast version of the license. And so California people tend to pick BSD when they want to license their software in this style, and Massachusetts people tend to pick the MIT license. The high-level overview of these licenses is that there are no additional requirements or stipulations attached other than these two things right here. You provide the software, anybody can use it for any purpose, and you also provide the source code. End of story. This is a, I'd say, a growing in popularity license, especially by companies. So Google, Facebook, Microsoft, the vast majority of open source code that these companies write and contribute to and use is licensed under either BSD or MIT style licenses. The sort of opposite end of the spectrum in terms of what an open source license is the GPL license. And under the GPL license, we have an additional requirement that if somebody modifies the source code and then distributes the resulting software to another person, so that could be like selling it to clients, or it could even just be like giving it to your friend, then there is this further requirement that they must also distribute the modified source code. So yeah, this is a little bit, let's say, I guess modern companies, Google, Facebook, Microsoft, they don't really like the GPL license as much because if they're modifying software, they often want to keep those modifications to themselves. The Linux kernel, the Linux operating system, is licensed under the GPL license. So it's, Google does in fact use a lot of GPL licensed software. Android operating system, for example, is based off of Linux. So it's based off of GPL licensed code. And Google does contribute back a lot of modifications back to the Linux kernel. But there are other companies, for example, NVIDIA. NVIDIA is a company that produces high-end graphics cards for computers. So if you're playing games or doing a lot of scientific computing or 3D rendering for movies, basically everybody is purchasing this hardware from NVIDIA. And NVIDIA is a company that has decided they will not touch any GPL licensed products. And so they do not contribute their the code for running their systems back to the Linux kernel. And there's a very big tension between the Linux community and NVIDIA because a lot of people want to do scientific computing on Linux, but NVIDIA's policies about the GPL make that more difficult. So those are the two, like if you only know two licenses, those are the ones to know. You'll see people talking about them a lot. This AGPL license is one other one that's a little bit different than the GPL, a little bit even more restrictive. And it says that, so if you create source code and create a program, and in any way, any user outside of you is using that source code. So let's say Google has created a new version of Linux that google.com is running. If Linux were under the AGPL license, Google would be required to make those changes back to the Linux kernel. But because Linux is under the GPL license and they are running their modifications internally for google.com and not actually, they're letting users connect to their modified software and use the modified software, but they're not distributing that modified software to consumers. That's okay with the GPL license, but the AGPL license would require them to give the software back, give their modifications back to the community. There's if you're in the like programming world, open source world, everybody has their own favorite license that they really, really like and are very sort of religiously devoted to their licenses. When I go to sort of professional conferences, research conferences, the vast majority of times people are very civil and nice to each other. You can have people, say, from countries who are currently at war, their militaries are killing each other, and they're very friendly at these conferences. But as soon as somebody starts talking about licenses, then people get really furious with each other. And I was at an open source conference once, and there was this heated debate between BSD versus GPL. Should machine learning software be BSD or GPL licensed? And people started throwing their sandwiches at each other. So that actually happened, and people get mad about license issues. Let's see. So yeah, there's a lot more licenses besides these. If you're a big project like Python, then you can create your own license and people will deal with it. Firefox is under the Mozilla Corporation. They have their Mozilla public license. Both of these licenses kind of sit somewhere between BSD and GPL. Essentially, they say that you're allowed to do whatever you want with the code, but you must describe what your changes are to people, even if you don't provide the actual code. But yeah, if you are creating your own projects, you don't want to create your own license. This is sort of lawyer territory, very complicated issues. Nobody will use your code if you don't use one of the standard licenses. And so these are the sort of the three categories that you really want to pick from. These GPL style licenses, there's a lot more of these GPL licenses besides just GPL and AGPL. But all of these licenses are commonly called copyleft licenses. The idea is that it's a pun on copyright, but copyright is for right-wing conservatives and copyleft is for hippie lefty liberals. So the GPL is very explicitly from a leftist movement. And a lot of the sort of theorists behind the GPL, the people who are talking about the legal theory and motivations and ideology, they're very explicitly come from a Marxist or communist background. One of the most famous of those people is, see, here we go, Richard Stallman. If you watch the videos, which I was plugging earlier, you'll see his face a lot. He's a very controversial figure because he's very, very opinionated, but this is the guy who sort of started the, so he wrote the GPL license and started the free software movement as we know it today. So examples of things that are not open source. So standard one, Microsoft Windows, you can do whatever you want with it, but you can't, you don't get the source code. You probably haven't heard of these two services right here, but both of these are multi-billion-dollar companies, Mongo and Elasticsearch. And both of these companies, they have what is called a source provided license rather than an open source license. And basically what that means is that they're going to, if you purchase their technology, they're going to give you the source code for their technology, but you are not allowed to actually do whatever you want with it. So in particular, Amazon used to offer Elasticsearch as one of their cloud provided web services, and that was cutting into the business of Elasticsearch because Elasticsearch was writing the code and then Amazon was profiting from it. And so Elasticsearch decided to change their license away from open source, away from anyone can use the software for any purpose, into a license where nobody else is allowed to make money from it except the Elasticsearch company. So one of the very common misconceptions about open source licenses is that you're not allowed to make money off of open source software, but that's not at all true. It's explicitly one of the core tenets that you can do whatever you want with it. You can charge as much as you want for the software, do whatever you want with it. If there's any limitations, like you can't use it for companies, then it's no longer open source. So there's a big discussion about this license file that's going to go into your repo. And what you'll have to do is pick one of these licenses, whichever one you feel is most aligns with your ideology of how you want people to use your software. And then you go to this link right here, choose a license, follow their instructions, and they will actually give you the text of the file to put into your repo. The very last thing is that there's this tutorial right here, which will walk you through the steps of actually creating the repository in the PyPy package index. And the only requirement, you can name your package whatever you want, it just has to be prefixed with this right here. And that way, other random people who are browsing the index will know that it is somehow related to this class. And since it's a class project, maybe not something that you want to base your company off of. Are there any questions about this assignment and either what to do or what I'm expecting? Okay. My guess is that this will be again, a relatively light homework assignment. There's no coding that you have to do. You might run into some slight Git issues here and some slight issues down here, but it's going to be nothing compared to the things you've had to deal with in the recent coding assignments. Lastly, on this week 13 folder, there are some files up here, a final sample.pdf and a final sample key.pdf. So a lot of people have been asking about what the final is going to look like in this class and how to prepare for it. So I wanted to give you this sample final so that you can better understand what to expect. The first thing I'll say is that for the final, you will have all of finals week to complete it. I'll post the final to GitHub on the first day of finals week, and then you'll have until the end of finals week to submit it. You're free to work on it at any point during there, start it, come back to it. There's no time limits, no sort of restrictions that way. You're also allowed to use whatever resources that you want, whatever non-human resources that you want. So you're allowed to use the textbook, you're allowed to use Google, Stack Overflow, any sort of internet resource. It's totally fine. You're allowed to open up the Python interpreter and type in commands. That's all totally fine. The only thing that you're not allowed to do is talk to a human about the exam. And so in particular, you won't be allowed to ask somebody else about clarification on a problem, or even asking other people if they've completed the exam or have been working on it. So my hope is that this structure, this framework, will be fairly low stress for you. You can do it whenever you want, no time pressure, and you'll also be able to put in as much work as you need to feel like your knowledge is fully represented and you get a good grade on the final. I'll also say that in terms of like how big of a percentage point-wise the final is going to be for your grade, I was originally anticipating that the final would be about 10 to 15% of your grade, but I've cut out a number of the labs from this class to try to reduce your workload due to this sort of online, a little bit more stressful environment. So we still covered everything, all the important topics, but a little bit of less points, a little bit of less work. And so because of that, the final is going to be about 20% of your final grade. The structure of the final, your actual final is going to follow the same structure as the sample final. That you'll start with this big table of big O notation, omega and theta, having to label all of these functions as to O versus omega versus theta. So it'll be really testing your knowledge of these concepts. And then there'll be a handful of true or false questions that randomly are just sort of test a whole wide variety of things from the class. And one of the things that I'll highlight about this section is that every correct answer will be +1 point, but the incorrect answers will be -1 points. So you really want to make sure that you are confident on an answer before marking true or false. Then there'll be some code snippets that somehow test your knowledge of lists and decks, so those data structures from a long time ago, and the different runtime characteristics of them. Here we'll have next a recursive function, and I'll be asking you to describe the recurrence relation for this function of its runtime, and then also using the master theorem to solve that recurrence relation. Finally, we'll have some code snippets related to the data structures that we've been talking about in the containers library. So like AVL tree, BST, heap, these sorts of things. And it'll be specifically asking you to compute the runtime of these code snippets. So we've talked about the details of how to do this, the runtimes of all of these individual functions, but this is the first time we've sort of seen it together in doing something, a set of code like this. What is the overall runtime of this set of code? And so you'll have something like this on your final exam. The last piece of your final exam I haven't put into this sample because it's going to be related to the material that we cover in the last 2 weeks of class related to the graph data structure and graph algorithms. So before the actual final exam, I will provide you a sample of that. But since there's been a handful of questions about the final, I wanted to get this sample final out to you right now without having to wait for that. Are there any questions about the final exam or how to study for it or what to expect for it?
Are we allowed to ask questions about the sample final to you?
Oh yeah, please definitely ask questions about the sample final. You're allowed to work with other students on the sample final. You're allowed to do anything you want with the sample final. There's no sort of grade associated with this. And I think I also forgot to mention that in the GitHub repository, there's not just the sample final, but there is a key for the sample final. So you can check your work that way. And yeah, feel free to. My recommendation is to not look at the key until you've completed the sample final, and then look at the key, check your work, and if you missed a question, don't understand why, then you can ask about it. Good question. Any other questions related to the final or grades or anything else about the administrative stuff with class?
Oh, we have a lab this week. I mean, like an
yeah.
extra lab.
So there won't be any, for the rest of the course, no extra lab assignments, just the homework assignments. I'll still be available during the lab times to answer questions, but I know everybody's very busy at the end of the semester and I don't want to needlessly add to your workloads. Okay, if other questions do come up, feel free to post them on GitHub or ask them in future classes. But today, for the remainder of our class, let's go back to our week 12 repository here, or week 12 folder. And I've added a new section down here on something called hash-based data structures. And this is actually, this hash-based technique is how Python internally implements their data structures, the dictionary and the set in particular. And so what we're going to do today is see some examples of situations where the AVL tree is sort of maybe not as good as we wanted it to be, and how Python works around that. So before going through these notes, I'm going to switch over here to the Python, to the terminal. And you can see that I'm in my containers repo on the Lambda server, and I currently have my solution to the AVL tree assignment checked out. As an aside, I think I haven't mentioned this yet, but I just recently posted the solutions to all of the last few homework assignments. So if you did miss something on some of them, you can, and you want to check how I did it, feel free to look at that. But yeah, so we have a working AVL tree in this repository right here. I'm going to open up Python like this, and we'll do from containers.avl tree import AVL tree. And AVL tree, just want to see what happens if we do something like this. So you see I'm passing a list in here, and there's a lot of duplicate entries in this list right here. And when I create my AVL tree, it's going to remove those duplicate entries. Now, what I'm going to do is do the same thing with Python's built-in set data type. And you can see that the built-in set data type does the exact same thing. It ends up removing the duplicate entries, and so it only contains one element of each of the things that were passed in here. And actually, our AVL tree that we implemented, it performs, or it has the same exact interface as this set function. So we could do something like, move my cursor to the beginning. Let's say s equals that, And for my AVL tree, A equals that. So S is my set, A is my AVL tree. And I can do something like 3 in S, get true, 3 in A, get true, 30 in A, false, 30 in S, false. I can convert both of these back into lists, list of S like this. For the AVL tree, we have to, let's see, I don't think we didn't actually do the generator for converting it into a list. That was one of those labs that I cut out for us. And instead we'll have to do a dot to list of an order like that, but it's the same thing, just called in a slightly different way. So this AVL tree and the set have the same interface. You can do the same things with them, but what we'll see next is that they have slightly different runtime performances, runtime characteristics, and we'll see that they have slightly different usability characteristics too. The first thing that I want us to think about is what sort of types, what sort of objects can we put into an AVL tree? Well, the AVL tree, when it's doing its insert, find, all these operations, what it needs the object to have, what it needs the value to have is like a less than, greater than, equals sort of operation. And there are a lot of data types in Python that support that. So we could do strings, for example. We could make an AVL tree out of this is a test like that. And then it's going to sort these things alphabetically for us. These strings, so recall that doing an alphabetic comparison of strings is less than this, A is less than is, and then test is in between is and this. And so that's why we get this order right here. If we wanted to look at the actual tree structure, we could do something like that. And that's what our tree structure looks like. And we could do the same thing too with a set. That a set and the AVL tree are so we can do the same things with them. Here it's doing it displaying them in a reverse order, but it's still sorted in some fashion. What I want us to see next though is something that's maybe a little bit more weird. And that's I'm going to create some lists, and we're going to insert those lists into the AVL tree. So have the variable xs1 equals 1, 2, 3 like this, and then xs2 equals 2, 1, 3 like this. And then let's see what happens if we do xs1 less than xs2. It gives us true. xs1 greater than gives us false. When you do these comparisons on a list in Python, it will go component by component, checking to see whether they're less than or greater than. And then as soon as it finds two components that are not equal, then it can return true or false. If we had, say, xs3 now equals 1, 2, 2, xs3 will be less than xs1 because these two match right here. But then this last one, 2 is less than 3. And then xs4 equals 1, 2, 4 like this. And xs4 less than xs1, false, because it's greater than, because 4 is greater than 3. So lists are something that you maybe don't normally think of as being able to do comparison operations on, but you can. And because you can put them inside of an AVL tree. And let's see what happens. AVL tree, xs1, xs2, xs3, xs4 like this. And that works perfectly fine. We can create an AVL tree out of lists. But now let's try doing this with a set. And you see that we're not allowed to do this with a set. There's actually a very good fundamental reason for this, but these sorts of errors can be really confusing to beginning Python programmers who haven't gotten this far in the data structures class. So we're now at the point where we can talk about why can a set in a dictionary support certain operations but not other operations. And we're going to answer that question by looking at what bad thing can happen when you put lists inside of an AVL tree. So we have these lists inside of an AVL tree. Let's make, we'll do AVL equals this. So there's our AVL tree. And I want to do AVL dot is AVL satisfied? That's true. And AVL dot is BST satisfied? True. So let's say it is a correct AVL tree that we have. It satisfies all of our properties. But now I'm going to do something that will seem totally unrelated to the AVL tree, but it's going to break the AVL tree. And in particular, I'm going to say, let's see, XS2 equals 0, 1, 2. So, whoops, that was the wrong thing to do. I wanted to do XS4 at 0 equals, well, let's see, okay. I did this, so let's keep with it. We'll see what happens. Let's reprint the AVL tree, and you can see that the AVL tree is exactly the same as it was before. When I created the AVL tree, like this, created it with XS1, XS2, XS3, XS4. Right here, I redefined the XS2 variable to be this list right here. But you can see that it did not affect my actual AVL tree. That's because when I did this, I just created a new variable name XS2 that gets assigned to this object right here. But if I, instead of creating a new object and assigning it to the name XS2, if I pick one of these objects, variable names like XS4, and I change the object that it currently is. So I'm not creating a new object and assigning it, I'm going to change it. I'll do XS4 at 0 equals 0 like this. And now, so notice up here, pay close attention to that AVL tree, and I'll print it out again. And now pay close attention to this AVL tree. And you can see that I've actually modified the contents of this element right here. This is different than this. And that's because here I didn't create a new object, I modified the existing object. And in our AVL tree, it's referencing the existing object. But now let's see what happens when I check, is BST satisfied? I get false. So previously, the AVL tree satisfied the BST property, but now I've done an operation that does not involve the BST in any way whatsoever. It does not involve the AVL tree in any way whatsoever. All I did was I modified a list, changed the entry in the list. And when I did that, because it changed one of the entries in the AVL tree as well, this is now in the wrong location for the AVL tree. I'm gonna do string of AVL like this so we can see here is our structure. And now I'm gonna go over and draw the AVL tree structure in the drawing program, and we'll be able to visualize exactly what happened maybe a little bit better. So my tree structure looked like at the top, let's see, make sure I do it right. At the top is 0, 2, 4. 0, 2, 4. And then to the left, 1, 2, 3, and to the right of that, 1, 2, 2. And to the right of that, 1, 2, 2. And then to the right of this up here is 2, 1, 3. 2, 1, 3. And this is what the current AVL tree structure looks like after I did that modification. And you can see, yes.
I think the 1, 2, 2 is on the far left.
Let's see, that would be correct. Yes, thank you. So yes, that is not there. It is 1, 2, 2 like this. Thank you for that. So this is our current structure of the AVL tree, and you can see that it's not satisfied because up here, 0, 2, 4, 2, 1, 3 is to the right of that, 1, 2, 3 is to the left. Previously, before modifying it, this 0 was a 1, and so it was satisfied, but when we changed it to a 0, that made it not be satisfied. So any of these data structures, whether it is a built-in data structure, set, dictionary, or a data structure that you're implementing, all of these data structures have problems maintaining the invariants, whatever those invariants happen to be, when the underlying data changes. When we change the underlying data of this AVL tree, the invariant no longer held. So that's the reason why this set data structure that's built into Python does not allow you to use lists as things that you can put into a set, because the list is something that could change at some point in the future, and that would break whatever invariants they need to have hold internally. We've talked a little bit about there are certain types that are mutable versus immutable. So mutable and immutable. Mutable meaning changeable, immutable meaning not changeable. And the list is an example of one of the things that's mutable, something that you can change. And so these mutable types cannot be inside of the inside of a set or a dictionary. We've seen some immutable data types as well. One example that corresponds to the list being a tuple. And so we talked about some of the runtime characteristics of tuples versus lists before, and they're actually very, very similar runtime characteristics. So you may have thought at that point, no reason to ever use tuples instead of lists. But here's the reason why you might want to use a tuple. If you want to put it inside, if you want to put your list inside of a set or a dictionary, you need to make it first immutable, like a tuple, before you can stick it in there. Another key immutable type is a string. Oops, a string. And so if we were to say, create a string x equals, this is a test, and do something like x at 4 equals a, we'll get this error that it does not support item assignment. And a lot of other programming languages have mutable strings. You can change a string after you've created it. There are a lot of good performance reasons why you might want to do that. It's very common to want to change a string by, say, adding a period to the end of it or fixing a typo in a string that somebody else has passed in. But in Python, the reason that they have decided to make strings be immutable is so that you can safely put them into sets and dictionaries without fear of bad things happening. Are there any questions about this sort of memory management issue or mutable versus immutable data types?
I have a question about the application with dictionaries. Is it that it doesn't allow lists as keys or values or both?
Great question. So for the dictionary, it requires that the key be immutable, but the value is allowed to be mutable. So you could have a dictionary with a dictionary of dictionaries where you have the values of the subdictionaries are further dictionaries, but you could not have keys be other dictionaries because dictionaries are mutable. So values can be mutable, keys cannot. Keys must be immutable. Good question. Any other questions at this point? Okay. So what we'll talk about next is how we indicate to Python that a type is mutable versus immutable. And that's also closely related to how the set and the dictionary are actually implemented in Python. So switch back over here and scroll down to here. Actually, before doing that, we want to do a little bit more code. In Python, there's a built-in function called hash, and this hash function converts whatever the input type is into a number. So if we have, say, a hash of Mike, that gives us this number right here, and then hash of Isaac, my new baby, gives me this number right here. And you can make your own data types support this hash function with the hash magic method like this. So any data type that has a hash method, you can use this hash function on it, and you would be able to insert it into a set or a dictionary. If you implement this hash magic method in your class, then you are telling Python that the values of this class will never change, that it's an immutable type, that no matter what, when you run this hash function on the type, you're always guaranteed to get back the same exact number out. And so the set and the dictionary use this hash function internally in their implementation. And what they do is they create a list. This list is sometimes called a hash table. And internally, they pick some size for this list. Typically, the size is some power of 2, so 2 to some I value here. And then when given a new item, so given a new X to insert, say, into a set, what they'll do is do the hash of X, and then recall that this is the modulus operator right here, which computes the remainder, mod the size of the hash. And this is the index that we place X in the list. So for example, we'll assume that our size is equal to 8. And let me just make sure there are 8 little entries in here. So there's 4, 5, 6, 7, 8. There we go. And if we come back over here, hash of Mike %8 gives me 4. Hash of Isaac %8 gives me 6. And so back over here, find position 4, and right in here we would put Mike, and then at position 6, put Isaac. This is a very fast procedure when things work well, that when things work well, all we have to do is call this hash function once, and then a lookup into a list takes constant time, O of 1 time, and so adding something is really fast. Checking whether something is in our set is also really fast. We just have to do this formula to look at the location or to compute the location. And once we find the location, that's O of 1 time again, check to see if it's right there. So really, really fast. That's only when things work well. And things are not always guaranteed to work well. And in particular, let's see if this still works. We do ASD. Oh, let's try. There we go. As %8 also gives me the number 4. So it gives me the same value as Mike. So this is called a hash collision right here. We have two strings that give me the same value back as my hash number. And that means that they both have to be located in that same entry in the list. So now we have, if we were to insert that as into this list, then we have Mike and as however many S's there were here. And so now when we do this lookup, not only do I have to do this computation here and look up the index here, but I also have to check all of the entries at that location to see if they are equal to what I'm looking for. In the worst case scenario, all of your entries, all in things that you've inserted into your list are going to hash to the very same exact value. And so you'll just have a big linear data structure that you have to loop over in order to do these comparisons. And so in the worst case scenario, you have O of n time for all of your operations, insert, lookup, delete. Best case, you insert into a entry, sometimes called a bucket in a hash table, insert into one of these buckets or cells, entries, and there is no collision. No other entry shares that same hash value. So you get O of 1 time, but if there's a lot of collisions, you might end up with O of n time. And so with that said, I want to take a look back at this Python time complexity link that we saw a long time ago. And so here's our list time complexities. We talked about these fairly extensively before, but we didn't really talk much about the set and the dictionary time complexities yet. And here you can see that for these operations like X in S, so again, this is calling the magic method, the element magic method, LM magic method, or the LM dunder method. And in an average case, typical case, no hash collision, you get O of 1 performance, but in the worst case, you get that O of n performance. Similarly for the dictionaries, in the, when you're doing a lookup in the dictionary, or really any of these operations, the typical case, constant time, worst case, linear time. In Python, well, let's see. I guess first of all, are there any questions so far about why these runtimes are the way they are?
What's the formal name of the hash table? Is that you saying that was a set?
Sorry, can you ask that question again?
Yeah, like when we were looking at the time complexities, did we, like what was, I'm on like the same website you're on now. Like what was the one for the hash? Is set like the hash table?
I see. We'd say that set and dictionary are the abstract data structures. So these sort of interfaces, and the hash table is the concrete implementation. So both set and dictionary are examples of a hash table. They're both implemented with hash tables. I don't believe they state that explicitly anywhere here on this page at least, but that is how they're implemented, and every Python implementation is required to implement them that way. So we've seen that this set, it could have been implemented with an AVL tree. We've implemented an equivalent thing using AVL trees. And actually most programming languages, so for example, C++ chooses to implement their sets and their dictionaries using AVL trees. but Python chose to use hash tables. Good question. Any other questions?
I have a question about how the decision was made to place an entry in the same slot in the hash table.
So that's a great question. Yeah, there's the cursor. So the formula for which index we place X into the list, so which slot it goes into, is given by this right here. And we have this hash function, and then we do the modulo, calculate the remainder with respect to size. So over here, when our size, for example, was 8, hash of this word here is 4, so it goes in position 4. Hash of Mike is 4, so it also goes into position 4. If we had a different hash function, then these things could go into different locations. Actually, designing a good hash function is a very complicated procedure. It involves really a lot of math. The computer science course that would typically go over this is possibly in a discrete math course. You might scratch the surface of it a little bit, but it's really a cryptography course that talks about how to implement good hash functions. Some of the properties that we want of a hash function are basically that the results seem fairly random. That first of all, if you provide the same input, you're going to get the same output every time. So over here, provide the same input, always getting the number 4. So it's not actually random, but it's basically random. That if I were to like change this just a little bit, so like a T instead of an S, there's no way to predict what this number is going to be out here. And this basically random sort of property is what roughly guarantees that you're going to be in a different slot when you do this formula right here. Did that answer your question, Jonathan?
Yes, thank you.
Great question so far. Any other questions? Okay. So yeah, in Python, the sort of takeaway summary is that Python's goal is really to be sort of user-friendly and to make it so that there are, I guess when you're programming, you're going to get bugs, and you're going to get lots of bugs. Very difficult to debug bugs, but we want to make those bugs sort of as simple as possible, eliminating as many classes of bugs as possible. And so the reason that Python chose to use this hash-based strategy is because it eliminates this class of bugs where if they had used the AVL tree and, yeah, it's too far up so I can't go back to it. But if Python had chosen to use the AVL tree, then anytime somebody uses it, they would have to be very careful never to modify any of those values ever again. Because Python chose to use the hash-based implementation, it guarantees that those invariants are never going to break, and so that they're always going to hold. Other languages, again, like C++, really care about performance, really don't really protect users from bad code nearly as much. And so it's much easier to get bugs in C++. You have to be a lot more careful with your programming, but you can get faster programs because of things like this. One last sort of problem about using hash tables is that they can lead to a lot of security vulnerabilities. And let's think about why that is. Let's imagine that somehow I knew what your hash function was. I know that you're taking whatever strings that I give you and sticking them into a hash table. Then I can maliciously construct strings so that your hash function is always going to return the same value. It's going to have a lot of collisions. And when I do that, your hash table that you're expecting to have good performance from is going to give you linear performance instead of constant time performance. And if I were to then insert a lot of these into your program's going to slow down, potentially crash. There are a lot. This is one of the most common sort of security vulnerabilities that happens in the real world. And if you're interested in security, here's 2 good links that describe some actual real world software programs that you've heard of that have had this happen to it. Okay, what we're going to talk about over the next 10 minutes or so is going to be a little bit more of an advanced runtime analysis. And this discussion, let's see, everything we've talked about so far is all fair game for the final. This next discussion, promise, won't be on the final, but it is something that's going to come up in practice a lot in your coding careers if you make a career out of programming. And so this is a little bit more advanced runtime analysis with the tree-based data structures versus the hash-based data structures. And here, what I want to emphasize is that when we've been talking about the runtimes of, say, the hash-based data structure so far, what we've really been talking about is the number of times that we call the hash function. So if we look at these tables right here, these tables right here are, or these entries right here are counting how many times we're going to have to call this hash function. It's not actually counting the overall runtime of our code. Again, one of the common misconceptions of Big O notation is that it's only related to runtime, but it's really related to anytime you're counting anything. And here we're counting applications of the hash function. Similarly, when we were talking about the runtimes of our tree data structures, we were really talking about how many times does the less than or greater than operation get called. And we, in particular, have not talked at all yet about what is the runtime of actually doing a less than or greater than operation, or what is the runtime of actually computing a hash value. And so we're going to talk about those right now. So first of all, for hash functions, they're guaranteed for any hash function, for any input, it's going to take time theta k, where k is the size of the input. So if we think about lists, for example, so let's do hash of Mike like this. That's super fast. So Mike times 10,000. Recall that in Python, if you take a string and you multiply it by a number, it just duplicates that string over and over and over again that many times. And so this is the word Mike duplicated 10,000 times. And you can see that the hash function on that's still pretty fast. But as we add more zeros at the end over here, it's going to slow down significantly. So for really, really large strings, if we had to put really, really large strings into some sort of data structure, things would be really slow. It'd be a second or so per string that we have whenever we're doing a lookup sort of operation. And that's not because the data structure is slow, that's because the hash function is fundamentally slow. Similarly, let's go back over here. Now let's think about the less than and greater than operators. Well, with these operators, in a worst case scenario, it'll take the same amount of time theta k, because in worst case, you have to compare every element against every other element. But if we were to say, compare the strings Mike and test, here we only have to look at the very first letter of these strings before we can determine whether it's true or false. And after we get to that first letter, it doesn't matter how long this string is afterwards. We can just instantly stop our program. So if we had, say, x equals Mike times 10,000 like that, and y equals a plus Mike times 10,000. Well, the very first letter between x and y is going to be different, and so this can return instantly. But when we hash x, it's still going to take a second to do that hashing value. Yeah, hopefully over Zoom, these delays are being manifest, but you can try it for yourself if you'd like on your own system, that these comparison operations here are much, much faster than the hash operations when you're at large strings. And so if we were to include these sorts of runtimes, both the runtime of the data structure plus the runtime of the hash or the comparison operations, we can get a little bit more correct understanding of the runtimes of our code. And in particular, the hash in an average case will be O of k, but in the worst case will be n plus k. In the AVL tree will be O of log n for the best case and O of k times log n for the worst case. So here, this O of log n, notice that it doesn't depend on k at all. So even in the best case scenario, the AVL tree really is faster than the hash table. And in the worst case scenario, it's a lot faster, log n versus n. So that's why these performance critical programming languages always choose the AVL tree over the hash table as their implementations, or as their default method for doing sets and dictionaries. Yeah, again, if this discussion is a little bit confusing, that's okay. That's not going to be on the final. But this is the sort of analysis that you would do if you went on to take a more advanced data structures course or an algorithms course. You would start really digging down into not just analyzing one property of your algorithm, but combining multiple properties together. And the more properties you combine into your analysis, the better understanding you can get, more factors you can trade off about when is one technique faster than another. So that's a sort of preview for upper division classes if you should choose to take them. Let's see, any questions about anything related to hash-based data structures? Okay, then we'll go ahead and end class a little bit early today. I'll stick around for the remainder of class, and then I have office hours. So if you have any questions about homework or anything else, happy to answer them then. Otherwise, I will see you all either tomorrow. We'll have the lab session tomorrow or next week.